All right. Does anybody know what this is? Okay, actually, let me show you a simulation. So everybody knows that this is a capacitor. Now you know that this is an inductor. So in this simulation, you can see that this capacitor is charged. So energy has been stored in this capacitor. Okay, so there's a store of energy, and now we'll switch this on. You all know what this is. This was a mass attached to a spring. And if this is on a frictionless surface, you store energy by pulling this mass across and then let go, and it'll oscillate forever. Okay, so if you store spring potential energy in it, that potential energy gets converted to kinetic energy, and this oscillates forever. Just like that, you see that in this circuit, in an LC circuit with no resistance present, resistance is the parallel of friction is resistance in electrical circuits. So this guy was storing energy in electric fields. This guy stores energy in magnetic fields, and the energy was oscillating back and forth. Okay. And this was an oscillating circuit, just like this. And if there is no resistance present, this will oscillate forever. And it has a characteristic frequency, and the frequency is, we'll show you in a second, the frequency of oscillation is omega is 2 pi f. F is the frequency. LC. F is how many times it oscillates per second. Okay. Is the linear frequency, and omega is just angular frequency. Okay. So where is that simulation? All right, so this thing oscillates with a frequency of omega, which is equal to square root of 1 over LC. So anybody know what this thing is used for? Has anybody come across this? Anybody? Have you guys heard of this?
No.
No?
No.
All right, so this is a basic tuning circuit. So this is at the heart of all wireless devices. Okay, so your cell phone is a wireless device. Okay, so when you call somebody and they get a wireless signal, this is the circuit that catches that signal in your cell phone. This is the circuit that catches the radio station that you're listening to. Okay, so all wireless devices, the wireless signal, the electromagnetic signal is being caught by this circuit. Okay. So your entire life is totally dependent on this circuit. Okay, at least the modern life. So this is at the heart of tuning circuit. Again, for any system to oscillate, you need to have two forms of energy. And if a system oscillates forever, then there's no dissipation. In this case, energy was stored oscillating between spring potential energy and kinetic energy. In this circuit, energy was oscillating between electric fields and magnetic fields. It was going back and forth between electric fields and magnetic fields. All right, so we'll get to that tuning circuit part in a second. Okay, so what we'll do is consider a fully charged capacitor. We'll charge this, here's a fully charged capacitor. So we stored energy in the form of electric fields. Initially all the energy is stored in the capacitor. And then this capacitor, this energy drives a current through the inductor. And so some of the energy is being transferred into magnetic fields here, and so on. And once in this, all the energy is being transferred there, and then energy is being transferred back to the capacitor. And that's the cycle through which you're going. All right, so here's the circuit. Now energy is all back in the capacitor, in the electric fields, and then it transfers back to magnetic fields. So you see. All right, are we back? Hello?
Yeah, we're back.
We're back.
Okay, can you guys see the screen?
No.
No.
Not yet.
All right, there we go. How's that?
Much better.
Yeah,
Brilliant.
It,
All right. Hundred megabits per second connection is what's advertised, and interruptions are 100 megabits per second as well. All right, so what we are doing is we are going to mathematically model the behavior of the system, okay? And generally mathematical model of the behavior of this system means writing a differential equation describing this system, okay? All right, so here's how you come up with this differential equation. Right now in this circuit, there's no resistance. Okay. So there's no resistance. So this is the energy stored in the inductor at any instant. So let's look at this instance where there's energy in the inductor and the capacitor. This is the energy stored in the inductor. This is the energy stored in the capacitor. Okay. And the sum of these two energies is constant. The sum of these two energies is constant. And so if you take the time derivative of that, that should be 0. Okay. So it's simple principles like that that gives us the differential equation. So let's, I'm going to derive from here to there. I'm going to go from here to there. And let me go to the whiteboard for that. Right, so. Okay, so the energy stored in the inductor was Li squared. And in the capacitor, it was Q squared by 2C, right? Yeah, Q squared by 2C. Okay. All right, so if you take the time derivative of that, that should equal 0. And by the way, IT is dQ by dt, okay? The current in the circuit is equal to the rate at which the capacitor is being charged, okay? So now we'll apply the chain rule, take the derivative of that. So that's I, 2I by 2 L di by dt plus 2Q by 2C dQ by dt equal to 0. Okay. Now I, of course, is, so the 2 cancels. I is dq by dt. L di by dt is d square q by dt square plus q over c dq by dt. Go to 0. So dq by dt cancels. Okay, it's 0 on, for most of the times it's not 0, so we can cancel that. Okay. So L d square q by dt square okay. And so now, so d square q by dt square plus 1 over LC q equal to 0. So there is a differential equation we've gotten for the charge on the capacitor, which models the behavior of that system. Okay, so what we'll do is, since L and C are positive, this is a positive quantity. So what we'll do is, to emphasize that that's positive, we'll write it as 1 over omega, as omega squared. Okay. Yeah. And this is exactly the same equation as that for a mass attached to a spring. Okay, the position of that thing obeyed this exact same differential equation. Simple harmonic motion. Okay, you guys can go check. All right, so the charge on the capacitor in this LC circuit is given by this differential equation, which is the same as this differential equation. Okay, so the charge on the capacitor is given by that. 1 over LC is defined as omega squared. And even Thai can solve this. And so the charge in the capacitor is given by Q max, sine or cosine omega t plus phi. Okay, so the charge on the capacitor changes sinusoidally. And you can take the derivative of that, and the current changes sinusoidally as well. Okay, so there's the amplitude of the charge, and there's the amplitude of the current. Okay. So anyway, this circuit has a natural frequency of oscillation, which is given by square root of 1 over LC. Okay. So here's how this circuit is used in all wireless communication devices. Okay. So at the heart of all those devices, and resistance is unavoidable. So here is resistance shown, and generally you tune the circuit by changing the capacitor. Okay. You could also tune it by changing the inductor. So whatever is technically easier is what you do. Okay, so this circuit has a natural frequency. You can change the capacitor. Here's a variable capacitor, so you can change the frequency. Okay, so let's say this circuit has a frequency of 100 megahertz. And there are multiple signals. There's a 100 megahertz signal, 101 megahertz, 102 megahertz, and so on in the room. Only the 100 megahertz, so if the driving frequency is equal to the natural frequency, it can set up large amplitude currents. So here's a 100 megahertz frequency that sets up a large current. All the other frequencies will not set up a large current in this circuit. Okay, and then the circuit picks that signal up. Okay, so again, let me make sure we understand that. So there's C, and I will draw without the resistor. Okay. So this is the antenna. And let's say this, the natural frequency is 100 megahertz. I'm just making up. Okay. Here is a signal with 100 megahertz. Here's 102 megahertz. And here's 98 megahertz. So you can have this room full of all kinds of signals, and only this guy will drive a large enough current. These guys will drive very small currents in this circuit. And that's how this circuit picks up that signal. So by the phenomenon of resonance, frequency, a driving frequency matching the natural frequency will set up large currents. Okay, so your cell phones operate, I don't know, it depends on the frequency, maybe 3 gigahertz or 5 gigahertz or something like that. Okay, so your cell phones are tuned to pick up the signal from your cell towers. Okay. Again, I can't emphasize enough, this is the heart of the tuning circuit, and it's at the heart of all wireless devices. Okay. So when natural frequency, where natural frequency of oscillation of the LC circuit is omega is 1 over root LC. Tuning circuits take advantage of this natural frequency with the phenomenon of resonance. Okay. Of course, resistance is unavoidable in real life. Okay. So here's how you come up, model an RLC circuit, a series circuit that has all 3 elements in it. When you have resistance present, when there's friction present. Okay, and so here's how it looks like. Here the resistance, inductor, and capacitance. What we'll do is, so we'll minimize resistance. Now what we have done is, when this thing is closed, we have charged the capacitor. Okay, so we've charged the capacitor. Now we'll remove the battery, and we'll let this circuit oscillate. Okay. If this resistance was not present, this would oscillate forever. But because the resistance is present, the stored energy is being converted to heat in the resistance, and you see the oscillations are dying out. So if you want to keep this circuit oscillating, of course, you got to pump energy in it. So how much ever energy you lose per cycle, if you keep pumping that energy in, it'll keep oscillating. Except for this circuit, the oscillation frequency is slightly different than when the resistance is not present. Okay. All right, so with the resistance presence, the energy stored in the inductor and capacitor is being dissipated. Okay, and that's the rate at which energy is being dissipated. So rate of change of this energy is decreasing, so that's why the negative sign. Okay, you can rearrange all those terms. So the behavior of this circuit is modeled by this differential equation. Okay, it's got a second order derivative, so it's a second order differential equation. It's linear because none of the terms are squared, so it's none of the time varying terms are squared. Okay, so it's a second order linear differential equation. And of course, you learn techniques to solve this kind of stuff in your differential equation classes. And here is the solution. Okay, so you see the amplitude of the charge in the capacitor is exponentially decreasing, and the amplitude is exponentially decreasing. That's what that dotted line says. Okay, this circuit oscillates at a slightly different frequency. This was the frequency, this would have been the frequency if resistance was not present. With the resistance present, the frequency of oscillation is slightly lower. And the larger the value of resistance, the lower the frequency. Okay, so the circuit is critically overdamped for R greater than RC. If R is too large, then the circuit won't oscillate. So this is a critically damped circuit. Okay. For low values of R, it'll oscillate. All right, so that covers this chapter. So what I'll do is I'll summarize it again. So this was the tuning circuit, and resonance just means that frequency that matches the frequency of oscillation of this circuit will drive this signal will drive a large current in this circuit. Okay. Okay, so going back to this, so if the natural frequency of this circuit was 100 megahertz, let's say you have many different signals, only the signal that matches the natural frequency will drive a large current. This will drive a very small current, this will drive a very small current. And then what you do is you take another inductor and the signal is transferred. So what you've done is you picked up the signal from this tuning circuit, you transfer the signal via a transformer to another circuit, and then process that signal in this black box. Okay. So again, this is the catching device, and then you transfer the signal via transformer, and or you couple it. Yeah, so via transformer, and then here's the processing circuit. All right, so let me summarize this chapter. Okay, so we started off talking with by mutual inductance. What we saw was if you had a circuit here, and if current changes in the circuit, that would mean that magnetic flux through this closed by circuit was changing, and you're inducing a EMF in closed by circuits. So changes in this circuit influence nearby circuits. And the coupling was called mutual inductance. Okay, so the coupling of the two circuits is mutual inductance. So EMF induced in the second circuit is equal to mutual inductance times the rate of change of current in the first circuit. You saw that a wire wound up in a solenoid will have a self-inductance. This acquires the property of fighting changes in current. If you increase current, it induces an EMF in the opposite direction. It induces an EMF to fight the increase in current. A decrease in current will induce an EMF which will try and maintain that current. Okay, so what you learned was if you wind up a wire in a solenoid, it acquires the property of fighting changes in currents. Okay, so the solenoid, if you increase current, will induce an EMF in the opposite direction. If you decrease current, it'll induce an EMF in the same direction of the current, trying to maintain that current constant. The self-inductance of the solenoid was given by that. For an air-filled solenoid, it's mu naught times little n squared. Little n is the number of turns per unit length, times the area of cross-section, times the length of the solenoid. So there is the inductance. Inductance are measured in units of henries, named after Mr. Henry. Okay. And this equation gives you the induced EMF. Induced EMF is minus L di by dt. Again, if the current is not changing in the solenoid, if di by dt is 0, the induced EMF is 0. Okay. You saw that in this circuit, when you close the switch, this was the mathematical model describing the behavior of this circuit. When you close the switch, and you saw that the current rises exponentially, the time constant of the circuit is L over R. The time constant is the time scales over which the current changes. Okay. So after one time constant, the current has risen to 63% its maximum value, and so on. And the current is exponentially building up. You saw that in this device, once when you flip the switch from here to there, you're removing the battery. And even after you remove the battery, the stored energy in the inductor is able to drive current through the resistor for a few milliseconds. Okay. And that current dies off exponentially. Okay, so the current driven by the energy stored in the inductor dies off exponentially. Okay. E by R is the initial current. We saw that, we said that energy is stored in the inductor in the form of magnetic fields. And so again, here's the equation modeling on the behavior of the system once you close the switch. And we saw that energy stored in the inductor when current I is flowing through it is 1/2 Li squared. And again, if there's no current flowing in the inductor, there's no energy stored in the inductor. The energy stored can be thought of as stored in the form of magnetic fields, the blue lines or magnetic field lines. And energy per unit volume in a region where you've created magnetic field is B squared by 2 mu naught. So remember this, anytime you have generated electric and magnetic fields in a region, you've stored energy in the electric and magnetic fields. So that's a useful way to think about it. Yeah. Transformers can step up and step down voltages. You can have step up transformers and step down transformers. Here's the input voltage and the output voltage across this resistor is given by this. V2 is N2 over N1 times V1. N2 is the number of turns here, and N1 is the number of primary turns. This is an oscillating LC circuit. If there was no resistance, this would oscillate back and forth forever. This would oscillate forever. The current would be going back and forth. Capacitors store energy in electric fields. Inductors store energy in magnetic fields. So again, this shows you the charge in the capacitor, and the charge on the capacitor oscillates forever and oscillates sinusoidally, and the current in the circuit also oscillates sinusoidally. Yeah. The frequency of oscillation, angular frequency, is given by 1 over square root of LC. And like I said, this is at the heart of all tuning devices, of all wireless devices. This circuit will pick up only the signal which matches its frequency. That signal will drive a large current in this circuit. All the other signals drive smaller currents. Okay. So this equation models a RLC circuit. So here's the dissipation, and with resistance present, the energy is dissipated, and the charge on the capacitor dissipates exponentially. Okay. The amplitude of the charge dissipates exponentially. All right, that finishes this chapter. I will pause now, and I'll let you guys ask questions.